also, I hope there is also, yes, I even managed to make my camera working, hopefully. Great. So, I will give basically two talks. First talk will cover the perspective of how can we use implementation attacks, side channel attacks to attack AI, so to attack, for instance, neural networks. And in the second talk, then I will basically switch and I will talk about how AI can make side channel attacks more powerful. So first one is CSI neural network, reverse engineering of neural networks architectures through EM side channels. Basically, this is a paper we presented last year at Usenix. So it's a joint work with Leila Batina, Shivan Basin, and Dirman Toyap. So I will give you quite a lot of information in next 2 hours. Do stop me if something is not clear, and I will try to make it at least a little bit more understandable. So, starting, why do we even care? So, first question is, why would we even care? Do we protect our machine learning, our neural networks against side channel attacks? Well, actually, there are many reasons. For instance, the simplest reasons why would you want to protect something like this is just think of it from this setting. You invest a lot of time in your machine learning model, in your neural network. So you trained, you spend a lot of manpower, a lot of time to make something that's very good. And then you want to sell that, but someone is able to simply reverse engineer it and obtain all the network. And basically, in a way, she is stealing your intellectual property. And as such, it's a question, okay, how difficult is to do that? How difficult is to reverse engineer neural network? And actually, there are many works. Yes, so performing adversarial attacks is easier if you have access to the model. That is also true. So if you have access to the model, it's very easy to do attacks. But the question is how difficult is to do that? So many people actually explored how can one use implementation attacks to reverse engineer neural network, but mostly those works all aimed at something special. So for instance, you have something very specific implemented in a specific way, and then you are able to use that optimization to attack. Here we asked more generic question and basically said, can we use the simplest of side channels? So quite generic in nature. And of course, yes, so trying to make the machine learning architecture more robust with GANs, that is possible, but what does it mean, robust architecture? So a machine learning architecture per se does not need to be robust or not. So the goal is just, can we attack it or can't we attack it? In essence, regardless how robust is your architecture, the effort to attack it with side channel attack is more or less the same. Unless your robustness comes from bigger network, then the attack scales linearly. So it's more difficult, but linearly more difficult. So what's cool about this attack is usually when people talk about side channel attacks, they always say, well, you use side channel attack to attack cryptographic implementation, to obtain secret key. And yes, that is the main or most popular reason, but actually you can use side channel attacks to get a lot of information. So either secret data, location, reverse engineer various stuff. So in a way, you already kind of saw reverse engineering with simple power analysis, where you were able to recognize the number of rounds or recognize the operations. And by doing that, you were able to get the key. But here we will actually talk about reverse engineering the architectures. So here I'm just writing a couple of examples what people did before. So for instance, they attacked convolutional neural networks via timing, via memory leakage, or you could exploit the line buffer in a convolutional layer when it's implemented in certain kind of way, and so on and so on. So here I will talk about reverse engineering neural networks, and there are so many different types of neural networks. So here I'm limiting only to 2 types of neural networks. multi-layer perceptron, and convolutional neural networks. Hopefully, you all kind of heard of those, but if not, do not worry, it's not so crucial at this point. What is important to mention is both of those types of networks are feed-forward network. So means there is no feedback loop. So how do we do reverse engineering of a neural network with side channel? Well, we first need to understand what do we want to attack. So neural network has many aspects. So anyone here never heard of neural network, never used neural network or something like this? Yes. Okay. So let me give you a brief just explanation what a neural network is, and do not worry. During the second lecture, I will go much more into details, so it will be much clearer. Neural network is just some, in this setting where we are considering here, it's just some set of layers where each layer is processing information. So your first layer is processing the input, your second layer would be processing the first layer, third layer, second layer, and everything that's connected, all the way to the last layer. And for instance, if you are doing the classification, your last layer would say black or white, or would say Hemingway 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's a just number of layers in processing. So basically, you are building a model of a data, and then you are saying, well, by using this model, the data should behave in a certain kind of way. And what is important to note, every of those layers has a number of neurons. Neurons are like nodes, basic building blocks of layers. So think of it in the simplest way. In the second lecture, we will be talking about using machine learning to attack, as an attack mechanism for side channel, and then you would put in every node in the first layer a single point of interest that Yossi mentioned. So in node, you put information, you put your input, and then processed input, and so on and so on. So already saying that, I already gave you a couple of elements you need to reverse engineer. So I said there are layers, I said there are nodes, and of course, to be able to build a complex function so that something that can map from any input to a number of outputs, you need to assign a number of weights. So each of your neurons will have a weight, will have a value that you multiply your input with that value, and then that value is giving you a better approximation of the correct answer. Additionally, you will have something that is called activation function. Activation function is basically a way how to make non-linear operations, non-linear correlations, because otherwise your neural network would be linear, so you would be able to process only linear information in the data. So for instance, that was in the 60s, where even the simplest XOR function was not was difficult to solve without using functions like that. What's our threat model? How do we do side channel attack? Well, when you're doing side channel attack, you first need to say what is your threat model. So we will be using only side channel information. So no active attacks, no fault injection, no nothing like that. We do not make any assumption on the input. So we do not care what kind of data do you put to the neural network. Someone say, yeah, my neural network works only with integers. Someone else will say, my neural networks work only with single precision floating points, this or that. Here, we do not care. Why? Because we handle all possible inputs, because we say they are all real numbers. And of course, something very important, we assume there are no implementations that have countermeasures against side channel attacks. So this is what you already kind of heard. There are ways how to defend against side channel attacks. Those ways are called countermeasures, and they are common in cryptographic implementations. So for instance, you cannot find today any real product that needs security against side channel attacks, and it will not be protected. But luckily or unluckily, however you want to look at it, machine learning implementations, machine learning algorithms are not protected with any countermeasures. Why? Well, because people are still not thinking so much about that perspective, how to protect machine learning against side channel attacks. Just as a note, even if it was protected, it would be possible to attack. The attack would be just more difficult to do. So what is the attacker able to do? Attacker is passive. That means he's able only to listen. So listen to the normal operation of a device. That means he's able to record, to measure power, to measure EM of the device while running the neural network operations, but he cannot interfere with the internal operations. So he cannot change anything. And the attacker does not know, of course, anything about the neural network, anything about the architecture, otherwise why would we do even reverse engineering? But what attacker knows, the attacker knows the input. And actually you can see this is a common assumption also in the attacks you discussed before. So for your side channel attack to work, you would need to know either the input, so the plain text going to AES, or ciphertext, depending, do you want to attack the first round of the algorithm or from the last round of the algorithm. And yes, since this is side channel attack, attacker is able to measure the side channel information leaked from the implementations. Implementations are simple devices, let's say something like Atmel or ARM Cortex. Why? Well, because those are the devices you would find in IoT settings, so Internet of Things settings. We were thinking, in what kind of setting can you mount side channel attack? Well, you need to have access to device. So one would say, could you make this attack on data centers with powerful GPUs? In essence, yes. But then there is always that question, how do you have the access to that data center, to those GPUs? If you have access, can't you do some better kind of attack? But in IoT setting, in setting where devices are basically in the wild, so sensors, actuators, there is no reason why you would not be able to approach the device and measure information from that device. So just a couple of reminders on, well, I will even skip this. Side channel attacks you kind of already covered quite a lot. And what's important to know is a little bit about more complicated types of attacks. So you talked about simple power analysis, and as I'm reading about correlation, about this and that, so there are those attacks, direct attacks, where you either make your attack based on the visual inspection of the data, like you did in your simple power analysis. You basically look at the power measurement, and then from that power measurement shape, you said, well, it looks like this, it looks like that. But there are more complicated types of attacks where you use statistics. The big difference in those attacks is you cannot do statistics from 1 or 2 or 5 measurements. You need a lot of measurements. So depending on the difficulty of the target, hundreds, thousands, hundreds of thousands, millions. And then the simplest type of the attack there, it's called DPA, differential power analysis. And just as a notation, high complexity, exactly. Just as a notation, depending on the source, if we are using as a source of the leakage electromagnetic radiation, the attack is called DEMA, differential electromagnetic analysis. But in essence, no difference. So it's just difference on the source, but the attack works in the same way. So how does it work? Well, you will cover the details next week during your lectures, but you will check for dependencies between actual measurements, so what's actual happening, and your hypothetical measurements. So you will assume some kind of model, and then you will say, well, if this model is correct, I will check all possible keys. And for the key that looks the closest to the real measurements, I will say this is my key. So in some naive diagram kind of way, it will be something like this. So you would have your input, your data, and then you have the real side channel measurements, what you are really measuring with your oscilloscope. and that has real key, correct, so secret key. And on the other hand, you have your model. So you already learned about a couple of different models. For instance, Hamming weight model. You would say my device leaks in the Hamming weight. You would say, well, if my device leaks in the Hamming weight, and if maybe the correct key is this one, I would get this output. You would do some kind of statistical analysis comparing the correct keys, so the real measurements, and your hypothesis. You would repeat that for all possible key hypotheses, and then you would take the most likely key hypothesis, the one with the best value, as the correct one. Now, you can do this kind of statistical analysis in many different kinds of ways. For instance, if you do the analysis with difference of means, this is what mostly people call differential power analysis or differential EM analysis. If you use, for instance, Pearson correlation, then this kind of attack would be called CPA or correlation power analysis. So this is just to explain. So here you would use Pearson correlation, and this is what we are using in this work. So in essence, our attack is CPA or SEMA, however you want to look at it. So let's start with the attack. This is just to show you on the left side, this is the microcontroller. So you can see we needed to mechanically decapsulate the microcontroller. Why do we do that? Well, the reason is simple, because when you decapsulate it, you are able to approach with your probe closer to the chip, and then you are able to get cleaner signal. So this is something that enables you to get better measurement. This is not a mandatory step. This is EM, yes. So everything here we are doing with EM. Simple reason is EM is more precise. So while power is giving you good information, but power is more on a bigger picture level. But with EM, you are able to get really precise information. How precise depends on your probe. So on the right-hand side, you have the probe we used. So these numbers, this name does not mean a lot, but this is quite precise probe. So you can really be very localized in your measurements. Yes, and this is how, is it E or H probe? I have no idea, honestly. I have no idea, sorry. I don't even, yeah, I don't know. So this is, yes, this is how the whole setup would look like. So you can see here, there is the board, the microcontroller. Here is the probe, and you have some oscilloscope to do the measurements. The better the oscilloscope, the better, well, the easier for you to do the procedure. So this is, let's say, fancy setup, let's call it like that. But actually, you would be able to use much simpler equipment and still break the target, reverse engineer the target. You would just need many more measurements. So let's start with the reverse engineering, the breaking of something. Well, how do we break stuff? You saw 2 slides ago, we said model. So we need to decide what kind of model of data our device will follow. And actually, since we are using the microcontroller, the common leakage model for microcontrollers is Hamming weight. So whenever you have microcontroller, a good guess, you want to start with the Hamming weight model. So this is what we also do. And basically there, the microcontroller loads the sensitive data to a data bus to perform any kind of instruction. So just as an information, you do the training phase offline, of course, and then we implemented the network in C language, compiled on the microcontroller, and this is just the expression for our Hamming weight. So depending on the number of 1 bits, we have different Hamming weights.